Happy Halloween, everybody. It was fun and very entertaining to see the costumes that some of you had today. So many props to those of you who livened up our days with your attire. We did not take a break and eat candy and chill out or anything like that for Halloween today. We continued to do math. Yeah. And we started by thinking about something healthy since you're going to have all that candy tonight. So we've got two data tables. Okay, the apples are healthy, the pizza's not healthy. But we've got two data tables, and I'm interested in knowing what's going on with these relationships. Are either of these proportional or not? So looking here, something that I notice is that there is not a whole number that I can multiply 2 by to get to 3. So there's not a whole number factor, but I can see if there is a decimal or a fraction that I could use. So I'm going to look at the ratio of apples cost to the number of pounds. So if there are $3 for 2 pounds, that would be the same as, let's divide by 2, we can scale it down that way, 1.5 per pound. 450 compared to 3 is also going to be 150 per pound. 6 to 4 will also be 150 per pound. And 750 compared to 5 pounds is also going to be $1.50 per pound. So that means I have a constant multiplier, which we would call that constant of proportionality, $1.50 per pound. That gets me from apples to the cost of those apples. So yes, this would be proportional. Yes. Now down here, based on this information, I've got some whole numbers. Yes, always nice. 2 times 6 is going to give me 12. So then I would need to see, is everything else multiplied by 6? Well, 3 times 6 is 18, so not 14. 4 times 6 is 24, not 16. 5 times 6 is 30, which is not 18. So these don't work, so no, it is not proportional. In fact, as I get more toppings, it gets cheaper per topping. Here, per topping would be $6. Or here, 14 divided by 3, it's only going to be something that's a little bit over $4. So it gets cheaper and cheaper as you go. So then I asked you to start thinking about equations. We're going to tie in what we know about equation writing with what we know about proportionality. And we looked at some conversions. First, we looked at conversions between degrees Celsius and degrees Fahrenheit. And you told me that several of you told me that you're familiar with degrees Fahrenheit. That's what we use generally to measure temperature in the United States. Less familiar with degrees Celsius. That's what is used in other countries. Often that's what's used in scientific methods. And that's not something where we know right away, 15 degrees Celsius, I know how that feels. If I saw 15 degrees Fahrenheit, I know that's cold. But if I see 15 degrees Celsius, I'm not sure. So there's a conversion equation that you can use. When you have your temperature in Celsius, so C, you can take it, multiply it by 9/5, and then add 32, and you now have the temperature in Fahrenheit. So as we go across this table, our rule would be times 9/5, and then plus 32. So 15 times 9/5. We had a couple different ways that people did it. One way was saying, 15 wholes times 9/5, which got them, once we simplified, 27. And then add 32, and that would be 59 degrees. Or some people chose to do 15 times 1.8, which would be 9/5 converted into a decimal. And that also gets you 27. Add that 32, and you get 59 degrees. So we had 59 degrees. When we do that with 20, same deal, you end up with 68 degrees. And with 30, same deal, you end up with 86 degrees. So is it proportional or not? We would need to have a constant multiplier, or the same unit rate, in order for this to be proportional. Looking here, we can say, well, what's that ratio of temperature to Fahrenheit to Celsius? 59 to 15. I encouraged people, rather than looking at exactly what it is, can we use some of our numeracy skills and be flexible and think, what is this close to? Well, 59 is close to 60. So we're close to 60 out of 15, or 60 compared to 15. And 60 divided by 15 is about 4. So this is about 4. Since 59 is less than 60, it would be a little less. 68 compared to 20, well, 68, you could say, if we're comparing it to 20, that's, I don't know, about 70. And 70 compared to 20 is about 3.5, because you would have your 3 times 20 to get to 60, plus another 10, which is half of 20 to get to 70. And then if we have 86, 86 compared to 30, oh, well, that's close to 90 compared to 30, which should put us close to 3. And since 86 is less than 90, it would be a little less. Comparing these, they are not the same. So there is no constant of proportionality, so it is not proportional. Now down here, we're taking our inches, n, and we're multiplying them by 2.54 to get centimeters, because we know inches are bigger than centimeters, so if you have 10 inches, you will have more centimeters. Well, 2.54 times 10 would give me 25.4 centimeters. 8 times 2.54, and 2.5 times 2.54. I don't even need to finish here. I can realize, ooh, I'm doing the same thing all the way. My rule was times 2.54. That right there is already my constant of proportionality. So yes, it is proportional because we have a constant of proportionality of 2.54. So then we looked at how those equations relate to each other. I had students make themselves a T-chart where we started with, well, we have proportional equations compared to not proportional equations. So our proportional equation of these two was C equals 2.54n. And our not proportional equation was F equals 9/5 C plus 32. Looking at these, well, we know a couple things. People told me that there's no constant of proportionality here. We know that if it's not proportional, and there is a constant of proportionality here if it is proportional. But I'm interested in the structure. And people noticed, well, in both of them, you're multiplying one of your variables by something. And it was China who said, well, maybe it's a fractions thing. But then she noticed that 9/5 can be converted to a decimal, just as 2.54 can be converted to a fraction. So it's not just whether it's multiplied by a fraction or a decimal. They both are multiplied by something. It seems that this adding on makes things different. So for the proportionals, nothing extra is added. And of these two, for the not proportional or the non-proportional, something is added at the end. And that led to a conjecture that if an equation has something added at the end, then it's going to be not proportional, or it will not be proportional. So students then came down and looked at these, and they applied that conjecture. They said, well, this one has something being added on. So my prediction is no. This does not have something added on, so my prediction is yes. But we've only seen one of each of those today. So we can't say that every single one is going to be like that. It's worth having some numbers to back you up. So I suggested make yourself an XY table where you plug in some different values for x. Let's just start, let's say x is 1. 8 times 1, because we know if two numbers are next to each other, we're multiplying. 8 times 1 is 8, plus 2 is 10. What if x is 2? 8 times 2 is 16, plus 2 is 18. What if x is 3? 8 times 3 is 24, plus 2 is 26. Well, from 1 to 10, that would be times 10. From 2 to 18 would be times 9. Those are not the same, so no. Here, if we have x, y, well, let's say x is 1. If x is 1, then y is 13. 1 times 13. If x is 2, 2 times 13 is 26. If x is 3, 3 times 13 is 39. So 1 times, 13. 2 times 13, 3 times 13. So yes, there is a constant of proportionality, and in that case, this is 13, which is that constant coefficient that we see in front of the variable x. Okay? So for your homework tonight and tomorrow night, you have some equations, some of which look like the ones we saw today, some of which look a little bit different. I want you to make a prediction based off of what you see, some structures. And then don't stop there. Then actually go through and say, well, if x is 2, what would y be? If x is 3, what would y be? Compare when we see y over x, that's like looking at for the unit rate. And we're saying, is there a constant of proportionality that you can find? I'll be interested to see what you do with these because we have some exponential situations. We also have some things where we have our x in the denominator. And so I'm curious to see. Have a safe and fun Halloween, and I will see you later.